Hey everybody, today I'm going to talk about today's Leetcode problem 1359, count all valid pickup and delivery options. I already solved this problem last night, but today I'm going to explain how I got to my solution. It's a little bit of combinatorics and math here. Kind of looks like dynamic programming, but you don't really need to do that much dynamic programming here. It's pretty linear, and we'll see how that works in a second. So the intuition behind this problem is that we can solve it recursively. Recursively in the sense that if we know the answer for n minus 1, we can use math to get the answer for n. So basically, we start with the base case of n equals 1, which is clearly just the pickup and then the delivery. So there's one answer. And suppose we want the answer for n. So first we can compute the answer for n minus 1. Given the answer for n minus 1, let's call it x. So x is the number of ways we can adhere to the rules and schedule the pickups and deliveries, such as there are n minus 1 pickups and deliveries. So there are x results for n minus 1. And let's think about one specific answer for n minus 1, like one specific setup. So like one specific answer out of the x different answers. Now to get the nth answer from the n minus 1th, we can just place the nth answer within the n minus 1th answer. So with the case of n equals 3, let's look at the n equals 2 answers. The key thing to note here is that it doesn't really matter where the third delivery is scheduled, as long as it's after the third pickup. So the rest of, we can place the third pickup and delivery wherever we want to in any of these answers, so long as the new delivery happens after the new pickup. So this is where the combinatorics come in. So you see how there's 4 items in each of these lists? Well, where can we put the new pickup and delivery? Well, we could put something here before everything, or in between each of the existing items, or we could put it after. So that's n plus 1, or sorry, that's if there's m items here, then we have m plus 1 slots to put an item, and we also have to put in 2 items. So first, let's assume that we can't put the delivery and the pickup in the same slot. Then we have m plus 1 options for the first item and m options for the second item. Now we also have to consider the possibility where we put the second one, the second pickup and the second delivery next to each other. So this would look like P3D3 right here. We could also do P3D3, 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 P3D3. So we have to add that to our solution as well. And this function represents the recurrence relation I've been talking about. So suppose we have I buckets, then we have I places to put the first item and I minus 1 places to put the second item. We divide that by 2 because we need the pickup to happen before the delivery. And since the pickup is either all after or before and not at the same time as the delivery, we can just use symmetry to divide the answer by 2, because exactly half of the time will our delivery be before the pickup in all the generated outcomes. Now, there's a second thing we have to think about, like I said earlier, which is, what if we want to schedule them in the same bucket? Well, then there's 2 times the number of buckets ways to do that, and again, exactly half of those, or I times, will the pickup be before the delivery. So now it's just a matter of dealing with the modulus. Basically, we start with 1 as our base case, and I represents the number of deliveries we last scheduled. So I starts at 1. We're supposing that we start with one pair of delivery and pickups already scheduled, and then we use our recurrence relation, or the slots function, to update our solution. And at the end, we'll have computed the result for n, because range is exclusive on the upper bound. We'll have computed the result for n using the result from n minus 1. So we can just return the result. So that's just one of many ways to solve this problem. And in my opinion, it's the most straightforward, because we don't really have to do anything crazy with a DP table, and we don't do anything with factorials directly. So I hope this clarifies a pretty straightforward, a relatively straightforward way to solve the problem. And I hope that you can go ahead and solve more cool problems like this. Thanks for watching.